So, welcome to this class on oligosynaptic and polysynaptic reflexes. So, what is oligosynaptic reflex? A reflex that involves more than one synapse, and so that means it could be 2 or 3. Polysynaptic involves many, more than 3. Okay. So, what are these and how are those different from monosynaptic reflexes? So, in this class we will talk about 3 things: oligosynaptic reflexes, we will have a couple of examples, we have discussed some of this earlier. Polysynaptic reflexes, we will have I think 1 or 2 examples for this also I think. Then flexor reflex or the flexor withdrawal reflex that was mentioned in one of the earlier classes will be discussed in some detail here. So, the classic example of the oligosynaptic reflex is the reflex involving the 1A interneuron. 1A interneuron. Let us remind ourselves what is the case. This muscle is stretching. If this muscle is stretching, then the 1A afferent gives command, not shown in this picture, is that it activates the alpha motor neuron of the same muscle. So, it will contract, that is one form of negative feedback, but this is a monosynaptic loop. This involves only one synapse, right. This is a monosynaptic loop that we have discussed in the previous classes. But what this 1A afferent also does is that it excites a 1A interneuron which inhibits the alpha motor neuron of the antagonist muscle. So, this is the antagonist muscle's alpha motor neuron. Why? Why does this do that? Because this stretching may be due to the contraction of the antagonist, stretching of the agonist, stretching of this muscle may be due to the contraction of this muscle. It is also possible that it could be due to other reasons, but at least this negative feedback ensures that if there is a need for that muscle to contract, the probability that it will contract will be relatively low in future or in the nearest future for the next few tens of milliseconds or hundreds of milliseconds. So, this involves one synapse here and one synapse there. This involves 2 synapses. We have seen this earlier. So, what does this do? This is inhibition of the antagonist muscle alpha motor neurons during stretching of the agonist. This is performed mediated by 1A interneuron, and 1A afferents serve as the sensor. So, this is the sensor and this is the interneuron that is causing this reflex. Okay. How do we know that this is an oligosynaptic reflex? How do you know that this is actually involving more than one synapse? So, what actually is done is the difference between, say, that monosynaptic loop and that oligosynaptic loop is actually of the order of 1 millisecond. It is actually between 0.5 milliseconds to 1 millisecond. Since we know, or slightly this way or that way, slightly less or more, since we know that the synaptic delay due to neurotransmitters can be between 0.5 and 1 millisecond, we know that there is just one more synapse that is involved. If there were 2 more synapses that were involved, then the delay will be higher by about anywhere between more precisely between 1 millisecond and 2 millisecond. Okay. So, this is how we know that this involves 2 synapses through classic neurophysiological methods. The case of the 1B afferent, what happens in this case is the muscle, say the agonist muscle, is contracting. When the agonist muscle is contracting, the Golgi tendon organ starts firing, that is the 1B afferent. Now, what would be an appropriate negative feedback for that? So, if the muscle is contracting, we should reduce the amount of contraction, but let us remember that all the proprioceptor neurons are excitatory by default. So, this 1B afferent excites a different neuron, an interneuron, which inhibits the alpha motor neuronal pool of the same muscle. So, this is again a disynaptic or involvement of two synapses. In the previous case, we saw the monosynaptic case. If the stretching is there for the muscle to contract, I can excite that alpha motor neuron, that is happening monosynaptically. But if the muscle is contracting, for it to contract less or reduce the amount of contraction or balance the amount of contraction, I have to inhibit that. That cannot happen through one synapse, but rather with it happens with the help of two synapses. Now, so it inhibits the alpha motor neuron of the same muscle, but what it also does is it inhibits the interneurons, which inhibit the alpha motor neuron of the antagonist, another layer of negative feedback. Now, what does this do? Every time this Golgi tendon organ fires, or if this muscle is contracting, in a way it is disinhibiting the antagonist pool, or is also slightly increasing the probability that the antagonist pool will be excited. Okay. So, this is inhibition. So, this is 1 minus and this is another minus, right? So, that becomes plus. At least figuratively we could say that it increases the probability that this alpha motor neuron will get excited. So, that means the force then that is produced by this antagonist will be in a position to balance the force produced by this agonist. So, that is the other way. So, there are two things that the 1B interneuron does. It inhibits the same muscle, homonymous muscle, and it disinhibits the antagonist or heteronymous, we will just say antagonist. So, it is not confusing, antagonist is disinhibited. Okay. This again involves how many loops, we said how many synapses. This disinhibition involves 1, 2 and 3 synapses, whereas inhibition of the same alpha motor neuronal pool involves 1 and 2 synapses. Okay. So, this is again another example of an oligosynaptic reflex. Okay. Now, what happens in the case of polysynaptic reflexes? Now, what happens is that sensory information from receptors, actually this could be any number, spindles, Golgi tendon organs, articular receptors, cutaneous receptors, so many of these, too many of these send information to interneurons in the spinal cord. I am just calling them spinal interneurons, and depending on the situation it could excite different muscles or alpha motor neurons of different muscles producing an output. In the previous cases we were able to describe the input output relationships with relative ease. In this case it is way more difficult to do that, because it is not clear what these things do. Actually the picture that is presented in the spinal cord is a mess, it appears like that, or at least when we examine that it appears like it is a complete mess. There is a whole network of interneurons that connect in various different ways. Let us remember that is provided for the purpose of flexibility, and that also reminds us of the limit of the classical neurophysiological approach. What is the classical neurophysiological approach? That is this, right. We excite one, for example, we excite this 1A afferent and study its effect on the other cases, on the case of that alpha motor neuronal pool, that alpha motor neuronal pool, that muscle, all those things we study, right. But that stops after about 2-3 synapses. After that it becomes it becomes like a black box. So, I am going to call this as spinal interneurons, they do something, there is depending. So, and also that means that the response is going to be less and less stereotypical as you travel from monosynaptic to disynaptic to trisynaptic to polysynaptic, right. The response becomes less stereotypical and more flexible, and the circuitry, neural circuitry that is involved becomes goes from simple to more and more complicated. Okay. And so, at approximately here the classical neurophysiological approach reaches its limits. Okay. And a classic example of a polysynaptic reflex is the tonic stretch reflex is this. Now, what is this? Let us remember ourselves, suppose a muscle is having a background EMG level, which is that. Okay. Suppose a muscle is having that amount of background EMG level, this is the background EMG level of the muscle, some non-zero activity, and then that muscle is stretched, its length is increased. If that happens, there is going to be an immediate response. So, we will have to see the time. So, the stretching starts with a very small delay, with that delta t there is going to be a response. That response we have called it earlier, this is a monosynaptic response, we called this earlier variedly as T reflex for mechanical stimuli and H reflex for electrical stimuli. This is the monosynaptic, classic monosynaptic reflex. It is given a different name, it is given phasic stretch reflex. Phasic stretch reflex, we will talk about what this means in a bit. Now, and then it settles, and then the length has settled at a new level, right here. Now, what happens? The response does not go back to here, that does not happen, this does not happen. What happens is that the response settles around here, but there is a difference in the previous background response versus the current response depending on the length. This difference is due to what is called as the tonic stretch reflex. This involves not a monosynaptic pathway, but rather a polysynaptic pathway involving several interneurons. And let us remember that, so that means what? That means tonic stretch reflex is the response of the system to a level change. The level of the muscle length has changed from one length to another length. For that the response, so if that is the level change, that is the response. If the level change was that much, the response will be that. For example, the response could be that much. If the level change was this much, then the response could be this much. So, the level changes, the tonic stretch reflex response will change. So, this is not exactly stereotypical. This becomes, I told you earlier that this becomes less and less stereotypical and more flexible. But not just that, there is more. Let us remember that this on the other hand is a phasic phenomenon, is it not? This is the monosynaptic response. The T reflex, H reflex is a monosynaptic response, which we call as the phasic stretch reflex. Engineers would call this as, this response is transient, whereas this response is steady state, is it not? This is what we would call, this is what engineers would call this as a response that is transient, that is going to last for a brief amount of time to a stimulus. So, in response to a stimulus that is going to last for a brief amount of time, but the steady state is due to other things, due to the level change, etc. So, approximately this can be called as a transient response and this can be called as the steady state response. Transient response is in this case H reflex or T reflex or a monosynaptic reflex or phasic stretch reflex, whereas steady state response is the tonic stretch reflex, which is response to a level of the stimulus. Okay. So, it turns out that the characteristic of the tonic stretch reflex could have important consequences for movement generation. How does this vary? We will talk about that in the next few slides or maybe in the next class. Another case of a polysynaptic reflex is the flexor reflex. So, suppose several receptors are there. These receptors sense a danger to the limbs, right. So, these are two afferents, free nerve endings, cutaneous afferents, together all these things I am going to call all these things together as flexor reflex afferents, FRA. Okay. Flexor reflex afferents, these they all send information about potentially dangerous stimuli to the spinal cord. So, there are interneurons in the spinal cord. So, these are spinal interneurons. These interneurons then react in such a way to cause flexion or withdrawal from the painful stimulus. We discussed this earlier, right, in the in yesterday's class, in the previous class, that if this is a nail and a person is touching the orifice, a hard body and the person is touching, there is withdrawal. That is not exactly a monosynaptic response, but rather a polysynaptic response. So, it could happen. So, what could be the delay that it could be approximately 40 to 50 milliseconds, whereas a monosynaptic response is usually below 30 milliseconds. Characteristic, if the response is below 30 milliseconds, you can be sure, approximately sure, can be almost sure that this is monosynaptic. If it is above 40-50, then you are talking about a polysynaptic response. So, and the response is also tuned to the properties of the stimulus. More danger, this could happen in more number of muscles. So, if the stimulus is perceived as more dangerous, then more muscles or more stronger alpha motor neuronal activation of the flexors will happen in such a way that the withdrawal can involve multiple limbs, multiple segments of the body. That means that there is going to be coordination of multiple muscles, because the muscles that perform flexion extension of the wrist versus flexion extension of the elbow and flexion extension of the shoulder are different, yet they all coordinate together to withdraw from the painful stimulus. So, that means there must be coordination between alpha motor neurons that send commands to all these muscles, and they all are controlled or given the command at approximately the same time by these spinal interneurons, right. Now let us say that the stimulation is happening at approximately that time, right, and the response starts at approximately that time. So, now that is the delay. This delta t is what I said is about 40 to 50, may change depending on case to case basis. Example, typically this is what happens. Now, what also happens is the case of crossed extension reflex and other things which we will discuss in future classes. So, for in this class, so what we have seen so far is the oligosynaptic reflex, which is 1A, 1B, etc. Polysynaptic reflex, this is the tonic stretch reflex, flexor reflex, okay. And another example of the polysynaptic reflex is the flexor reflex, okay. So, with this we come to the end of this class. We will discuss the other cases in the future classes. Thank you.